Welcome everybody to another edition of the GT podcast. We are your hosts Divya and Abhishek, and today the topic of our podcast is going to be thermal management, and we're joined by Brad today. Thank you, Brad, for agreeing to be our guest. We're excited to talk about this topic. It surely is a buzzword these days, so it would be nice to have some perspectives on what exactly is thermal management and how it's influencing engineering design these days. To start off, can you talk about who you are, what you work at GT?
Sure, yeah. So my name is Brad Holcomb. I've been at GT since 2009, and I've been part of the thermal management team that whole time. So thermal management is really about controlling the temperatures of the components of a vehicle or any kind of system. And also for vehicle design, you have to consider the temperature of the occupants as well. So it's all of these different systems which work together to heat the vehicle on cold days, cool the vehicles on hot days. So my background, I went to Purdue University. I have a master's degree from there. I focused on component cooling, so computer chip cooling. But here at GT, I've been looking at larger systems since 2009. And you're right that it's a really important topic for engineering. Recently, combustion engine vehicles have been making large advancements in fuel economy, and thermal management is an important topic, or important part of that, because if you can warm up the vehicle to its ideal operating temperatures quickly, then you can reduce the friction in the engine to increase the fuel economy. So that's been kind of a driving focus for our thermal management simulations since the time that I've started. Now with the large shift to electrification across a number of different industries, there's been some new challenges that have come up. And again, thermal management is an important part of those systems as well, just trying to manage the temperatures of all the different components.
Nice. That sounds like a very comprehensive answer. Thanks, Brad.
Yeah. You did half the job for us for introducing the management topic.
And from what you described, it does seem very important. And I think you are ideally poised to talk a little bit more about how we shifted as a company, GT, from doing IC engine thermal management to what you said about electrification. I know you already gave a summary of that. Would you be able to talk a little bit more about what important differences you found when considering thermal management challenges for IC engine vehicles versus what we are seeing becoming more prevalent today, especially as this probably mirrors the shift in what GT simulation software is being used for and how we evolved?
Sure, yeah. So thermal management systems here at GT have always been focused on complete vehicle systems. So an engineer might start with a standalone model of their thermal management system where the heat load from, say, a combustion engine is imposed on the system. And then they're modeling the coolant pump, modeling the valves, modeling the heat exchangers. If they're doing a single-phase system, if they're doing a two-phase system, they'd be modeling the compressor, the evaporator, condenser, expansion valve. But then they're also simulating the load from those various systems. Now, the thermal management system, because it links so many different systems together, in a combustion engine's vehicle, you'd have the combustion engine itself. You'd also have the oil lubrication system, because that's cooled by the coolant system, which then rejects heat to the environment through the radiator. You might also have a transmission oil system, which could also have a heat exchanger with the coolant system as well. So these different systems are linked together. And if you're looking at fuel economy of a combustion engine vehicle, you're often looking at that over some specified driving cycle, whether that's an EPA regulated driving cycle, some standardized world driving cycle. For larger vehicles, maybe some specialized load cycle. Other systems, you might have some transient operation that you're trying to simulate. So in order to simulate those transient effects, you do want to link in these other systems to your thermal management system. So instead of just having an imposed heat load for the combustion engine, for example, you might have the actual engine performance model running alongside the thermal management model to provide updated boundary conditions. For the lubrication system, instead of having a constant oil temperature and a constant oil flow rate, you could model the oil pump, you could model the oil bearings as well to give you feedback on how much oil flow you actually have, how much heat from friction you actually have being added to the oil, and what kinds of temperatures you're looking at over the course of this driving cycle. So, and then of course, for a vehicle driving cycle, you would actually want to model the vehicle as well, understanding what type of performance demands it has on the engine to be able to achieve the target driving cycle. Maybe you need to be at full throttle for certain periods of acceleration or part throttle for cruising. Maybe the engine shuts off during part of the cycle. So linking all of these different systems together was very important in a combustion engine vehicle. So with the shift to electrification, the thermal management system is again at kind of the center of the model as well, because you now have all of these different systems that are providing heat to the thermal management system, but you need to just manage their temperatures in a little bit different way for an electrified vehicle. But again, at GT, we've been focused on being able to do very detailed subsystem models, but link those to a complete system model so you can study the interaction between different systems. So that's been important for both. I guess you had asked about some of the differences between the combustion engine vehicles and the electrified vehicles. I think the main thing is for a combustion engine vehicle, you have the engine itself, which is producing quite a bit of heat. And so you can use that heat effectively to warm different components. So the heat actually helps to warm up the oil and warm up the coolant as the vehicle's coming up to temperature. You can use this warm coolant to warm the passengers if you've got a cold day and you need to provide some heat to the cabin. So you can just run that through a simple heat exchanger in your cabin and provide that heat to the occupants. And so you have this large source of waste heat that can be used. In an electrified vehicle, the electric motor is much more efficient. The battery is not producing as much heat. So you have less waste heat that can be used to warm up the passengers and warm up the occupants, warm up the different systems in the vehicle. So you have to be more careful about how you manage the energy because you don't have this high temperature source that you can use to provide warm coolant to your different components. Another key difference is, the heat for the cabin, I guess, has to come from the battery in the electric vehicle. So you could have a resistance heater, you could have a heat pump system, some other type of system, but that energy that you're using to warm up the battery itself, warm up the passengers, is directly impacting how much range you can get out of the vehicle. So there's an increased focus on efficiency there. And then probably the last big difference is the operating temperature of the various components. Batteries tend to like to be at around room temperatures. So they tend to operate between 20 Celsius and 40 Celsius. So, room temperature operating conditions. But what that means is that you might have to cool them down on a hot day. You have to warm them up on cold days. And then, you don't have this engine that's producing a lot of heat that can give you free energy that can be used to warm up the battery. So it has to come from somewhere. Yeah, well, it's not free. It's energy that's wasted as heat that you're then harvesting to not have to run a resistance heater or something. But the electric motor, that tends to operate up to around 130 Celsius or so, whereas the combustion engine can operate up to like 160, 170 or so for the metal temperatures there. So yeah, you've got some different demands on the system and generally more efficient components. So you have to structure the system in a little bit different ways.
Yeah, I think you touched a great point where, both of them are so different in the sense electric and IC, where why thermal management is now the center focus for electric vehicles is because all the energy we spend on heating the passengers and also the other heating systems it all comes from something that you have to produce energy for. And would you say that that's when system simulation plays a very significant role? I know in IC engines too that it's important, but especially now that we are focusing on generating this heat as now a resource more than a waste heat, it's more important.
Yeah, I'd say it definitely is important for system simulation. If you're looking at the range of a vehicle, it's not just about how much energy is stored in the battery pack and how much energy you need to run the electric motor to move the vehicle, how much energy you can recover, as you're braking using regenerative braking instead of just friction braking. The second biggest consumer of energy in an electric vehicle is the passenger comfort system, the battery comfort system. It's the same, it's the thermal management system. So being able to optimize how much energy you're using for that system for various modes of operations, various environment conditions, affects your vehicle range, so you can meet your range targets for the vehicles. If the consumer's considering two vehicles at a similar price point, and one has 250 miles of range and one has 300 miles of range, then they're probably leaning more towards the 300 miles of range. Most people don't drive 300 miles in a day. I drive probably 25 miles a day. So I would theoretically be fine with like a 50-mile range electric vehicle. But
is real.
Yeah, but I'm not interested in buying, spending $40,000, $60,000, however much, on a 50-mile electrified vehicle. I'm interested in something that has that additional capacity for when I want to take that road trip, I don't have to stop every hour to recharge the thing.
I'd be surprised if any company charges $60,000 for a 50-mile range.
Well, that's true. If you're looking at that kind of range, you're probably looking at something like a plug-in hybrid, which has the range extender on it and gives you that flexibility. But yeah, so it's people still have range anxiety. People buy vehicles for maybe not what they need 90% of the time, but try and buy a vehicle for 100% of the time. So if they can get that extra range out of the vehicle, that's a better value to them as a consumer. I forget what the statistic is, but some of our customers have commented that like each additional mile we can add of vehicle range adds like X $1,000s to the price that we can ask for this vehicle. So there's definitely a value proposition to being able to design an efficient thermal management system so you're able to use a higher percentage of that battery capacity towards actually propelling the vehicle down the road.
Yeah, being an EV owner myself, I can say that the driving experience in winter and summer is dramatically different. So that definitely is something, contributes to choice.
I think one other thing that probably is important as well, besides just individual consumers, when you're looking at electrified fleets, thermal management can scale your efficiencies dramatically. And when you're looking at not just single vehicles, but across, let's say, thousands and thousands of vehicles, for example, in delivery vans, in semi-trucks, I think the savings would be massive, both in terms of energy efficiency as well as emissions.
Energy efficiency. Yeah, exactly.
So
yeah, that's the thing. If you're running a delivery company with electrified vehicles, having that additional few miles of range means you can buy a fewer amount of vehicles to cover the same territory. So yeah, it's definitely important and definitely something that is good for sales and marketing, both at a consumer level, but also for fleet vehicles as well. It's a good point.
And lesser downtime on charging as well, right? So each mile also contributes a lot more on time.
It's true. I think, depending upon the use case, right? Like, so with your vehicle, if you've got a charger at home, you can charge it overnight. But the amount of battery pack that you have to fill up probably depends on whether you need a faster charger at home or you can just plug it into the wall. With a fleet service, yeah, it's about your power demands for what the fleet's going to need to recharge all the vans so the next morning they're ready to go.
And I think for those fleet kind of cases, I would assume the stationary charging system also has thermal management on it to ensure that you don't overheat your battery or whatever system you are charging. So I'm assuming for those kinds of things, it's not just the vehicle, it's the charging system itself that also needs to be thermally managed. And I'm assuming we can do a lot of simulations there to get them to be more efficient as well.
Yeah, definitely. Yeah, you if you've got a fast charger that the stand that you're plugging into, that could generate a lot of waste heat for the power electronics, and so that might have to be actively cooled. or certainly require a large passive heat sink to be able to maintain the operating temperatures. So yeah, as you're doing the energy from an AC system to a DC fast charge, then you would need to have those power electronics managed, and that is a simulation that we can do.
I guess if we start talking about each aspect of thermal management, podcast will.
Yeah, exactly. So. I think here at GT we've tried to design our system to be very flexible. So we have base components that you can link together. For the thermal components, you can have a heat input source that's just a control, so it can come from some transient profile that you've measured. It could come from some electrical model in GT of your system that's generating the heat, and that can come from a detailed source, can come from a lookup map, any number of different sources. So we've got a number of building blocks that you can put together that you can link your thermal system with these other systems, link with the flow solution as well for an actively cooled system. You can really build out the detail in your simulation while still maintaining a fast running model.
I think Divya is our resident developer for thermal management. So
one of them.
Yeah.
But I think you touched on a great point there too. We can not only do multi-physics but also multi-fidelity.
Mm-hmm.
So even if you have different building blocks in the system, modeling different systems, we can choose where we want to go detailed, where we want to go a little bit coarse. Can you talk about that a little bit more?
Yeah, sure. I think when you're looking at these different components, you do want to manage the level of detail in your model depending upon what the system model is going to be used for. So for a battery pack, for example, if you're running a detailed battery pack simulation, let's say you're running a fast charge simulation, for example, and you want to understand if you're putting 200 kilowatts of energy into this battery pack, what are the individual cell temperatures going to look like? Are there going to be any cells that are not accurately cool or not effectively cooled by the cooling system that we've designed when they've got this much energy coming to them? So for that level of detail, you might want to have some more detailed finite element components. You might want to have a very detailed flow model so you can look at the coolant temperatures in your different systems. You'd want to model the battery casing and all of the surrounding materials and really model the conduction from one part to the next so you can get an idea of what your temperature field is over your entire battery pack. Now, if you've got a cell that's not being cooled effectively, it's going to be running at a hotter temperature. That's going to be aging the battery cell. So we can link that with an electrochemical model to understand how these charge and discharge cycles age the cells unevenly and ultimately reduces the lifespan of your battery pack because maybe you're not getting the same performance out of cell number 1 compared to cell number 50 that's in the middle of the pack and being cooled more effectively. So we can run these detailed component models in GT, and we can run them with some specified boundary conditions. You can link them into the system simulation, and we're making a lot of efforts to speed that up. It might run at 10 or 20 times slower than real time, which is still pretty reasonable for a system simulation, but not something that you might want to have for a control simulation. So one of the challenges, especially with EV systems, is you have a lot of different systems that you need to link together. So, for example, you might have a heat pump system that's responsible for heating and cooling the cabin. That same system might also be responsible for heating and cooling the battery pack. So, depending upon what the battery pack needs, depending upon what the cabin needs, you might have control valves to kind of direct this cold coolant or this warm coolant around to the different components. You might have the same loop or a separate loop that's also used to cool your electric motor and power electronics. So there might be some cases where you want to harvest the energy that's coming from the electric motor and power electronics and put that energy into your battery in your passenger compartment to warm it up. There might be other times where you need to cool the motor and power electronics, but your battery and passengers are at a comfortable temperature, and so you don't need to be providing that heat. So you need to be able to, lose that heat to the environment effectively. A fast charge simulation or a fast charge system on a cold day would be an example of where you need to provide heat to the person who's sitting in their vehicle while it's fast charging for 30 minutes, but you need to be able to cool the batteries because they're being fast charged. They've got a lot of energy that's being put into them. They're generating a lot of heat. So your system needs to be able to handle both cooling the batteries and heating the occupants at the same time without overheating your occupants or overcooling, your batteries, or the other way around. So there's a lot of challenges in terms of controls for these: when to open which valves, what speeds to run the pump at, how to handle this efficiently. So you want to be able to run ultimately a fast system model that can respond in real time. And this can let you hook up your model to a software-in-the-loop system where you can run your actual controls logic, feeding the controls inputs to the GT model. The GT model provides that back to the control software in real time. And ultimately a hardware-in-the-loop model where you take the physical controller that you're going to be installing in the vehicle, and rather than hook it to your prototype system, which is really expensive to make, you can hook it to your GT model, which can provide you that realistic feedback of what the system's going to do when this control input changes to, say, vary the pump speed, for example. What does that do to the battery temperature? How does the controller need to respond to that? So a hardware-in-the-loop model can give you that real response from the calibrated model back to the controller without having to build out the full test bench for your full complete vehicle system.
Yeah. And so, shameless plug, we wrote a paper for the Purdue conference where we were simulating exactly that kind of system and made it faster by replacing the refrigerant or two-phase loop with a machine learning model. And this is literally what you're talking about. It was a full EV thermal management system, and we got the model to become at least, I think, 30 to 40% faster. So if people want to check out that publication, it's on our website.
But yeah, that's a big focus. So being able to take your model that you already have to simulate the detailed components and then have some steps to easily go from that model to this real-time capable model so you can hook it into your control environment. That's something that used to require rebuilding large sections of your model. But we've done some simplification steps. We've got some tools and workflows within the software to reduce the fidelity of the model. Maybe that does involve replacing part of that with a machine learning model to simplify the physics a bit. But it's kind of this gradual scale between the level of detail that you can get and the model speed that you can get.
Oh, so Brad, I think we can probably move to the next section, but I know you talked a lot about the different levels of detail you can get for an electric vehicle, especially focusing on the battery. Since you mentioned you can have an electrochemistry model, we can have a finite element component model that can connect to your thermal management system for fast charging or even during a drive cycle. So it seems that a lot of it is focused around batteries, especially the thermal management system. I think one of the issues I've seen, at least in the news, that is quite popular is batteries catching fire, especially in scooters or electric vehicles. Or I think there was even a case where a ship caught on fire when it was transporting a lot of electric vehicles. So it seems then that this is very important. And can you talk a little bit about what might be the cause for these, and if modeling, especially thermal management, how that is associated with these kinds of things?
Yeah, absolutely. Yeah, so I think vehicle fires in both combustion engine vehicles and in electrified vehicles are an issue that you have to be concerned about. With combustion engine vehicles, you've got this hot engine, you have a lot of other flammable fluids in the engine compartment, and so if a hose breaks or something, and it contacts the exhaust, the vehicle can catch on fire, or you can have electrical issues or everything else as well. With the electric vehicles, the components aren't operating as hot of temperatures, so it's not really a concern about something coming into contact with something else that's combusting necessarily. But you do have issues with what's called thermal runaway in your batteries. Thermal runaway occurs if a battery has some damage. So if you get like a nail puncture, some damage to the battery pack itself, that can cause an internal short circuit. You could also have some manufacturing flaw in the battery cell itself that causes an internal short circuit or some method of the battery producing heat. So as the battery continues to produce heat, it will continue to warm up unless it's not being effectively cooled. And you can have issues where these reactions that are occurring inside of the battery, you could have like the separator between the anode and cathode. If that melts, then now you have the anode and cathode coming into contact with each other, and it's going to cause more heat to be produced. These reactions also tend to accelerate at higher temperatures. They're an exponential function of temperatures. So as the reactions are occurring, as the battery's heating up more, the reactions actually speed up more and produce more heat at higher temperatures. And so that can cause thermal runaway within a single cell. I think just because of the manufacturing challenges, and with so many millions of cells being produced, you really have to design the battery pack in a way that if thermal runaway does occur in one of the cells, it's not going to propagate to neighboring cells, or it's not going to propagate outside of that module. It's not going to propagate to your whole vehicle. So, as this cell produces heat, it can cause other cells which don't have this damage to also start reacting in this way and, releasing the energy that's stored in the battery as heat. And so it can cause this kind of chain reaction throughout your whole battery pack. So that's kind of what thermal runaway is. And when you see these electric vehicle fires that hit the news, it's because, one cell had an issue and then that spreads to the neighboring cells in the pack. And then all of a sudden you're releasing all of this chemical energy as heat on the vehicle. And because the cells continue to produce heat, it requires a lot of water to put out. It's really challenging to deal with this.
Water, but I thought chemical fires, you need some other form of extinguisher.
There's a number of different methods that can be used, but essentially you want to just remove as much heat as you can to slow the reactions down, prevent other cells from going into thermal runaway if they haven't already. And so large quantities of water are a good way to remove lots of heat from a vehicle. Sometimes, salt water, I guess, could be used because that can also short out and prevent, other cells from releasing their energy. So there's a number of different methods that could be used. Special extinguishers are also a possibility as well. But it depends on where the fire is. If it's at an energy storage location, maybe you do have some specialized system that you've built into the grid storage, for example, to extinguish that kind of fire. If it's a fire truck rolling up on a vehicle that's on fire on the side of the highway or in front of somebody's house or whatever, they might not have the necessary tools. So just being able to, again, remove as much heat as possible from the vehicle is the best way to extinguish the fire. But it certainly is a challenge, and it's something that we want to be able to simulate within GT. So within our electrochemical battery cell, we can model these runaway reactions as they're occurring. You can have different reactions for different battery chemistries. You can monitor the temperature of the battery as it progresses, monitor the reaction rate, the species that are contained in the battery cell and kind of how those progress, so how the reaction continues depending upon the size of the cell. And this can be linked to a thermal management model as well. So we might link this electrochemical model to a finite element model of the battery cell. So we're able to look at the maximum temperature in the battery cell and how that drives the thermal runaway reaction, how the neighboring battery cells, how they heat up or cool down depending upon what's happening within the battery pack, and how that allows this to propagate or be contained depending upon your active cooling and how you've designed the battery cell. So these simulations tend to be quite detailed, and that's kind of along the lines of this like 20 to 30 times slower than real-time simulation that I talked about. So it's for the very detailed models where you're considering all of these individual millions of temperatures inside of your battery pack that takes a while to run. Certainly you would want to simplify this model for a system level model, but I think for the thermal runaway model, you're looking at that more detailed approach.
Those kind of detailed models is what is useful for modeling this very complex system, right? Because you need to focus on the cell level, and also it's a very transient, highly transient and dynamic problem. So that explains also why, the amount of detail that goes into the model translates into 20 to 30 times. But coming in from me also personally as a developer who works on thermal FE, we do pretty detailed modeling with thermal finite element, modeling all the temperatures and heat rates. And when you actually put it in a system with a lot more of 1D models going on, and you have all different physics and also the details, you have to focus on the cells, especially in thermal runaway, because one cell can propagate into different chain reactions. So I think 20 to 30 is very reasonable, and we also have a lot of exciting new developments that we are working on to make the speed a lot faster. And I think that's also an ongoing development that we have.
Oh yeah, definitely. Yeah. People, it's important to be able to turn simulations around faster. If you have to wait 3 days for a simulation to finish, you can't spend that time necessarily iterating on your design because you don't know what the answer is. Whereas if you can turn that around in an afternoon, in an hour, however long you need, then that allows you to make design decisions faster, to be able to shape the direction, try different system approaches, try different cells from different suppliers, all these different things that go into designing these battery systems. You can make those decisions faster, you can get accurate results, and you can turn simulations around quicker. I think one of the unique things that we do is being able to rely on some 1D fluid flow for certain components, not having to model the 3D CFD. So we might calibrate the flow in a 1D system to detailed 3D results. But for these transient problems, we can use a 1D approach, which allows the fluids to be solved much faster. And so your model is going to be run much faster than in a comparable 3D CFD approach.
Yeah, coming from a 3D CFD approach, our runtimes are like lightning fast. But then when you look at it from someone who's only modeled 1D, and when they add a 3D FD component, it might look slower. But as you say, it's only a matter of hours and not days.
It's true. Yeah, different engineers are going to come at it from different time perspectives depending upon their background. There are still situations where you would want to run a detailed 3D model to really study the physics of the fluid flow in great detail. So this is kind of a complement to that, to be able to do your design iterations and turn them around much faster.
Yeah, accuracy versus fidelity to simulation time. Exactly.
The vent gas is one of those situations where, depending upon the level of detail that you want to model, you might model that in 3D CFD, or you might model that in a 1D flow tool. The vent gas is important because as these reactions occur, they do generate gases that need to be vented. The products are combustible, so you can get a situation where the cell's producing this vent gas, and if it ruptures and starts venting on the neighboring cell, now you have this hot gas that's impinging on a perfectly fine cell that can cause that cell to go into thermal runaway. Or this gas can propagate, and if there's a spark or something else from something else that's happening, that can cause this gas to catch fire, and then that continues your propagation. So it's important to model that, and if you really want to look at the details of how the flow is impinging on a neighboring cell, maybe that's something that requires a higher fidelity simulation. If you want to model it more in a general sense and be able to track your species in different regions of your battery pack, that's something that could be done with a 1D approach and could be done much faster.
Okay, so can we put whatever reaction we want in our thermal runway model in GT if we want to do that? Or?
Yeah.
Okay.
Yeah, so the method that we've chosen is a very flexible method. You can define your different reaction species. You can define the reaction mechanisms. It's the same approach that we've used for engine aftertreatment systems for years. That same chemistry solver, we're just applying it to this new problem. And then the template itself that we're using to model the battery pack can be connected to a flow system, so the vent gas products that are produced in these reactions can be vented into the flow system. So you can model pressure buildup, you can model a valve opening to model the vent gases, you can model your network of flow components to represent the air volumes in different regions of your battery pack and track these species. We can also do combustion reactions in these different pipe and flow split components to model what happens if this gas catches fire, how much energy will be released based upon the products that are in the gas. So yeah, it's a complete chemistry simulation that you can define depending upon your battery chemistry.
It sounds like a lot of things going on to model thermal runaway. You have chemistry, flow, thermal, everything you can think of. And it's also interesting to see how philosophies from engine design can also be applied to electric vehicles. So that's quite interesting.
Yeah, it's something that has required a lot of collaboration within GT from different groups bringing their expertise on different parts of the problem to be able to solve this together. It really is benefited by our system level approach to model building in that all of these components could already work together already. We just had to put them together into this easier to use template. So that's something that we've recently released with version 2023. And so, that's available as a release candidate now, or build one will be available for people to use. And so it's something that we expect customers to be able to start using right away to model this thermal runaway reactions.
That's probably a lot about thermal runaway.
Yeah.
Divya, do you have any more questions for Brad? Or?
No, I think now would be a great time to actually show some of our viewers what a thermal management system might look like. Brad, would you be okay doing like a short demo on things a GT thermal management model might look like?
Yeah, sure. Yeah, we could do that. All right. So on the GT website here, if you go to the Industries and Applications tab up at the top, there's a thermal management section with a number of different pages here that you can go to. I'm going to highlight a couple of them here. The first one will be the electric machines and drives. Let me zoom in on this so you can see a little bit better. It's probably good. All right, so this is like a very detailed finite element model of an electric motor. And really what you're looking at is the individual temperatures of the different components inside of the electric motors. Now, the heat source for this could come from a variety of different sources within GT. It could come from a simple lookup map giving you the overall heat rejection of the motor under different operating conditions. You could actually break that down with like an FEMAG or a JMAG model to give you the individual heat sources within the stator, the windings, the rotor, all of these different internal components. But you can model this detailed temperature field within the motor. You can look at different cooling concepts for the housing. You could look at like impinging jet flow for cooling the windings. There's a number of different things you can do with this detailed motor model. For powertrain cooling, this page is more focused on engine heat distribution for combustion engines. Again, using this same finite element solution to be able to model the temperatures in different components inside of the engine model. So you can build this detailed model. You can study, what amount of combustion heat is going out as exhaust, is going to your coolant, is going to your oil, is warming up the structure, and really model the warm-up of these different components over these different driving cycles. On the battery side, let me zoom back out a little bit here. We have this simulation of thermal runaway, where you can see runaway was triggered in the upper left-hand corner of the cell here. I think it'll repeat here in a second. But the runaway is triggered, and you can see how that propagates out to the different cells in your battery pack. So we talked about this is something you want to avoid, but of course you need to be able to simulate it to understand how you can mitigate the runaway propagation.
That looks really good.
Yeah. And then the last section, looking at kind of vehicle systems as a whole. So we've gone through the individual component models, but looking at different system layouts, you can see we're comparing two different cooling loops here with different heat exchangers, different systems that are built in. So understanding how these affect your vehicle range, how these affect your passenger comfort, how these affect the temperatures of your different components, but also looking at how many components you need and how much that's going to affect your vehicle cost. I mentioned earlier, increasing the range of the vehicle can net you a certain amount of additional cost per vehicle or an increase in the vehicle price. But if that's offset by needing more than that in terms of components to achieve that range, then it's not cost effective for your vehicle design. So all of these pages are available on the website. There's more details about it. And of course, you can contact us if you have any additional questions. So thanks for having me on the podcast. It's been great.
Thanks, Brad. That was really nice. And it's been really fun discussing this. And yeah, just know that if you are considering an EV, there are a lot of engineers working to make sure that the energy efficiency and thermal management are the best that it can be with all of the tools that we have. So it's been really fun. Yeah, thanks for joining.
You're welcome. Thanks so much.
Yeah, and yeah, to all our viewers, so wherever you're listening to, do subscribe to us so that you can be updated when new episodes release. But until next time, thank you from me, Divya.
And me, Abhishek.
And Brad, thank you.